All right, let's do something a little ambitious today. We are going to build a complete geometric intuition for machine learning, starting from absolute scratch. You'll see how everything, from a simple line of best fit all the way to a massive neural network, is really just a different way of exploring a complex, high-dimensional landscape.
You know, to really get past all the hype, we have to start with the most basic question of all. When we say we want a machine to learn, what are we actually asking it to do? The answer, it turns out, is all about geometry. At its very heart, all of machine learning is basically a search for the lowest point in some kind of high-dimensional landscape. So let's unpack what that really means.
Okay, just look at this data. A machine learns this pattern by finding a mathematical function, in this case, just a straight line that best describes the relationship. See? It's not magic. It's really about formalizing the underlying geometric shape of the data itself.
This whole process can actually be broken down into a universal four-step game that literally every single machine learning system plays. It always starts with data, which are just points. Then you choose a model, which is basically your guess about the pattern. Next, you need a loss function to score just how wrong your guess is. And finally, you use an optimization strategy to systematically make that guess better.
So try to imagine every possible guess your model could make. We can actually plot the badness, that's the loss, for every single one of those guesses. What you get is a surface, a landscape, where the lowest values correspond to the best possible models.
So learning is really just navigating this landscape. The most common way to do this is with an algorithm called gradient descent. It just calculates the slope right where it is and then takes a tiny step in the steepest downward direction. It's this simple, powerful engine of just rolling downhill to find the best answer.
Okay, so let's move on to our first set of tools, classical models. We'll see how this whole landscape idea plays out, but more importantly, we're going to see where they fundamentally break.
So this is the simplest tool imaginable in our learning game. A linear regression model, well, it can only make one kind of guess, a straight line. Yeah, it's a pretty rigid tool, but for data that actually follows a linear trend, it's incredibly good at finding that low point in the lost landscape.
Now, this very simplicity introduces a really fundamental tension. We call it the bias-variance trade-off. A simple model like our line has high bias. It's just biased towards seeing a straight line and will totally miss any complex curves. On the other hand, a model that's way too flexible has high variance. It'll fit the noise in the training data perfectly, but then completely fail when it sees new data. The real goal is to find that perfect sweet spot right in between.
And this is the critical question, isn't it? What on earth do we do when our data's true shape is complex and, well, not a line? A straight line is a terrible guess. This single problem is what drove decades of research and leads us straight into the modern era of AI.
For a very long time, the answer was just brute force. If your model couldn't find the pattern, then you, the human, had to go in and manually create new, more informative inputs from the original data. This process, called feature engineering, was a total art form. It required massive domain expertise and created this huge bottleneck in progress. Now we get to the paradigm shift. Let's look at the elegant, powerful solution to this problem. A totally new kind of model that learns the features and the patterns all by itself.
Instead of trying to fit a rigid line to messy, complicated data, a neural network does the exact opposite. It takes the very space the data lives in and just warps it, bending, stretching, and folding it until that complex pattern becomes simple. Often, it warps it until it's something a simple line can separate. And this whole transformation happens in this two-step dance, repeated layer after layer. First, a linear transformation stretches, squishes, and rotates the coordinate system. Then, a nonlinear activation function performs a fold. By stacking these layers, a network can learn this incredibly complex high-dimensional origami to untangle pretty much any pattern you throw at it. And backpropagation, that's the messenger. It's what travels backward through the network after a guess. It carries a signal, the gradient, that tells each layer exactly how to adjust its little stretch and fold operation to help create a better final outcome and, of course, to move downhill on that loss landscape. But of course, this incredible power isn't free. The very depth that makes these networks so expressive also introduces its own set of really profound engineering challenges. So that core mechanism, backpropagation, can be really unstable. As that gradient signal travels backward through many, many layers, it can either shrink to almost nothing or just explode into an enormous value. This is the infamous vanishing and exploding gradients problem, and it can literally grind the whole learning process to a halt.
A huge breakthrough actually came from designing better activation functions. The older ones, like the logistic function, they have these flat parts at 0 and 1, which causes the gradient signal to just die. Modern functions like LU are specifically designed to not have those flat spots, so the learning signal can flow freely.
Honestly, taming deep models is a whole discipline in itself. The modern toolkit is full of tricks, like smarter weight initialization, which helps start the search in a good part of the landscape. There are normalization layers to keep the signal stable, advanced optimizers that can adapt the learning rate, and regularization methods like dropout to stop overfitting. All of these are just designed to manage the very delicate process of training these deep networks. Okay, wow, we have covered a lot of ground. Let's try to consolidate everything we've talked about into a few powerful, reusable mental models that you can pretty much apply anywhere.
So here are the 3 big takeaways. First, always remember that all learning is just traversing a landscape. Second, think of your models as geometric tools. Some draw lines and others are space benders. And third, never forget that model depth is a double-edged sword. It offers incredible power, but demands incredibly careful engineering.
Theory and intuition are amazing, but the only way to really make this understanding stick is to build, to experiment, and to see for yourself where and why things break.
So here is your path forward. Start with a project. Build a network to separate that 2 moons dataset, and just watch it learn to bend space. Then, run an experiment. Train a model into total oblivion, and visualize its decision boundary as it starts to overfit to pure noise. And finally, here's a question that's still at the frontier of research, one that builds right on our landscape analogy. Why does gradient descent work so well in practice, even when these landscapes are insanely complex and non-convex? The answer, well, it's still being discovered.